Welcome back to The Explainer. Today, we're wrapping things up with our course summary of Part 2, bringing everything together into one clear visual journey. We're going to take those complex mathematical models and physical failure mechanisms and distill them down to figure out the true anatomy of failure. We're talking about why things break, exactly how they break, and most importantly, how we can actually predict it before catastrophe strikes. Let's get right into it.
Here's our visual syllabus for today. We'll be covering 1. The mechanics of failure, 2. Brittle versus ductile fracture, 3. Linear elastic fracture mechanics, 4. The threat of fatigue, 5. Tracking cumulative damage, and 6. Material testing and prevention.
Part 1. The mechanics of failure. Understanding the fundamental flaws.
If you sit down and calculate the strength of the atomic bonds in a piece of steel, it should theoretically be able to withstand almost 25 times its actual engineering strength. Crazy, right? But in the real world, it absolutely doesn't. And the reason is simple. True perfection just doesn't exist. Literally every material contains minute, microscopic flaws. So the absolute crucial point here is understanding the split in our anatomy of failure. On one side, we have the immediate catastrophe of fracture. This happens when a pre-existing flaw gets hit with a massive sudden overload, splitting the material instantly. On the other side, we have the slow, creeping danger of fatigue. This is progressive. It happens under fluctuating, cyclic loads. Think of a machine constantly vibrating or an airplane pressurizing over and over, where a microscopic crack just slowly creeps along until the part simply cannot hold together anymore.
Part 2. Brittle versus ductile fracture, the microscopic evidence.
Before we even touch the math, you have to see how materials physically pull apart. Under an electron microscope, the difference is night and day. On the left, we've got a ductile material tearing. See all those dimples? Materials like aluminum alloys or low-carbon steels undergo massive plastic deformation before they fail. They stretch out, creating these tiny voids that link up and leave a highly textured surface. But then, look at the brittle fracture on the right. That is cleavage. The material just separates sharply along specific crystallographic planes, with practically zero stretching. It's a sudden, glass-like snap. And honestly, from an engineering standpoint, that's terrifying, because it happens without any visual warning whatsoever.
Part 3. Linear elastic fracture mechanics, predicting the break.
So, this brings us to the mathematical framework we use to predict exactly when a crack will become unstable. Because if we know a flaw's in there, we absolutely have to know how much load it can take before it violently runs away. Instead of getting bogged down in heavy derivations, let's just define fracture toughness, represented by TIC. Think of it as the ultimate balancing act. It balances the stress you're applying to a structure against the size of the microscopic flaws hiding inside it. If your applied stress and crack length combine to exceed the material's fracture toughness, well, the crack runs away, and the part fails.
This Ashby chart brilliantly illustrates where different materials fall on the spectrum of fracture resistance. Up on the y-axis is our fracture toughness. Way up at the top right, you'll spot our tough engineering alloys. Your steels, your titaniums, your aluminums. They can handle large cracks and huge stresses without completely failing. But check out the bottom right. That's where you find technical ceramics and glasses. Sure, they might be incredibly stiff, but their fracture toughness is terrible. A tiny microscopic scratch on a piece of glass is usually all it takes for the whole thing to shatter under tension.
Now, there is a bit of a catch with linear elastic models. Mathematically, the equations predict that the stress right at the infinitely sharp tip of a crack is, well, infinite. But obviously, materials cannot handle infinite stress. So, to actually predict failure in highly ductile materials, engineers rely on Irwin's plastic zone correction. What happens is the material right at the crack tip actually yields and stretches plastically, creating this tiny microscopic bubble of deformation. Irwin figured out a super neat trick. You can adjust your math by simply pretending the crack is slightly longer than it actually is, just adding the size of this plastic bubble to the real crack length. It's brilliant because it lets us keep using linear equations for ductile materials.
Part 4. The threat of fatigue, the slow killer.
Okay, let's transition away from sudden overloads and talk about fatigue. If fracture mechanics is about knowing the absolute breaking point, fatigue is about everyday operational wear and tear. I love this famous anecdote about a ship's cook because it perfectly captures how insidious fatigue really is. The cook noticed a crack in the steel deck, and every time the ship hit rough weather, which is a cyclic stress, that crack grew just a tiny bit longer. So he just started painting dates on the deck to track it. Eventually, the crack reached a critical length where the stored energy was enough to sustain tearing on its own. The ship literally broke in half. That is fatigue in a nutshell. To quantify this slow damage, engineers use SN curves to map out exactly how many cyclic stress loads a material can survive before giving way. You've got stress amplitude on the vertical axis and the number of cycles on the horizontal. Notice how for some materials, the curve drops but eventually flattens out into a completely horizontal line? That right there is the endurance limit. If you keep your everyday cyclic stress below that line, the material can theoretically vibrate back and forth forever without ever developing a fatigue crack.
Part 5. Tracking cumulative damage, predicting the end. In the real world, a component doesn't just experience one perfect, constant vibration. An airplane wing, for instance, gets hammered with huge stresses during takeoff, moderate stresses during cruise, and sudden, random jolts during turbulence. So how do we add up all that microscopic damage? Enter Miner's rule. Engineers use it to mathematically sum up the fractions of a component's structural life that get consumed over time. You just take the number of cycles the part actually experienced at a certain stress and divide it by the total number of cycles it could survive at that stress. Add them all together for every stress level into a variable we call C. And when C hits 1, 100% of the fatigue life has been consumed, and failure is basically guaranteed.
If you want a chilling reminder of what happens when we underestimate this, look at the de Havilland Comet in the 1950s. It was the world's first commercial jetliner, but several of them tragically broke apart mid-flight. The culprit? Square windows and rivet holes. Those sharp corners perfectly concentrated the cyclic stress from the cabin pressurizing and depressurizing on every single flight. It launched microscopic fatigue cracks that grew completely unnoticed, cycle by cycle, until the fuselage violently tore apart in the sky. It changed aviation safety forever.
Part 6. Material testing and prevention. Safety in the real world. So how do we guarantee the materials we're using actually match these mathematical theories? We can't just blindly trust blackboard equations. We have to physically break things in the lab under highly controlled conditions. We use standardized notch specimens, like the compact tension specimen here. We intentionally machine a hypersharp crack into a block of metal, hook it up to a massive hydraulic rig, and literally rip it apart. By meticulously measuring the exact force it takes to make that pre-existing crack jump forward, we derive the actual, physical fracture toughness for that specific batch of material.
But hey, remember Irwin's plastic zone we talked about earlier? For highly ductile materials, those linear elasticity models totally break down because the material just stretches way too much. So we use alternative physical tests like CTOD, crack tip opening displacement. Instead of just measuring the pulling force, we physically measure exactly how far the crack stretches wide open before it finally begins to tear. It is a fantastic, incredibly precise measure of how well a ductile material resists failure.
We've covered the jump from instantaneous overload fractures to the slow, crawling menace of fatigue, and explored how we use rigorous math and destructive testing to keep our world safe. As we close out this course summary of Part 2, I want to leave you with one final thought to ponder. If the math fundamentally proves that every single material is flawed at a microscopic level, are engineers ultimately just brilliantly managing an illusion of perfection? It's a pretty wild reality when you look at the physical structures all around us. Thanks for joining me for this explainer, and keep questioning how the world around you stays intact.